So, we just finished doing this thing on the PV diagrams, and here we have a whole bunch more PV diagrams. There's some language that we need to know, because in questions they'll often just characterize changes by using technical terms, and if you don't know the technical term, you won't know what they're talking about. So I used to blow this stuff off because, you know, I was concerned about the math. And so then I'd get a question, I wouldn't know what the question really talk about because they'd use some technical term and I wasn't clear on it. There's four that I want you to know about. If we talk about an isothermal change, it means thermal, basically temperature. Isothermal change follows one of these isotherms. And for an isotherm, there's no change in temperature, and we linked changes in temperature to changes of internal energy. That's what we said before. It's not equal to it, but if the internal energy goes up, the temperature goes up. If the internal energy goes down, the temperature goes down. So if there's no change in temperature, I know this internal energy, the change in my internal energy is zero. So that means that for this type of change, the amount of heat that I put in must be balanced by the amount of work that I take out. 10 joules in must be balanced by 10 joules out because the sum has to equal zero. And I can say, well, in that case then, my work is equal to the integral of P dV. My work is equal to the integral of P dV. Agreed? So some real ramifications there by simply saying, oh, it's an isothermal change. Oh, by the way, it's an isothermal change. That means your temperature didn't increase. That means that your internal energy didn't change. That means that your heat and work balanced each other out. There's an awful lot in that one term. And I didn't follow it. I didn't, oh, what the heck, it's just another term, you know. Isobaric, we use isobars for measuring pressure, so isobaric means constant pressure. Well, constant pressure is actually not that significant for other ramifications. I still get that my internal energy, my change in my internal energy is equal to the Q plus the W, and all I can say is that because this is a nice flat-topped relationship, that my work simplifies into the pressure times the change in volume. Mathematically, it's still this, but it simplifies to that. Notice it's a constant pressure times a change in volume, not a constant volume times a change in pressure. And for people who don't like to draw diagrams, it's easy to get those two things confused. For people who draw diagrams, you know, when you don't have a change in volume, you don't have any area under the curve, which we'll see next. So next is isovolumetric, same volume. In this case, because no work can be done, there's no change in volume, so no work can be done, then work is equal to zero. My pen just disappeared. Work is equal to zero, which means that my first law of thermodynamics changes to, well, the work's zero, so it goes away. So it simplifies to that. And then the last one, the one that I had kind of most trouble with, was adiabatic change. And what that means is no heat in or out. You can change the volume, but you don't have time to get the Bunsen burner on it or to put the ice pack on it. So for that, Q, well, really, Q is the amount of energy. Q is equal to zero. So that goes away. So we end up with that as the statement of the first law. We can still do the internal energy. We can still do the work, and the work is that, though the expression for this guy is not the same as the expression for the isothermal. Different equation. I would like you to know, well, first of all, If you want an isothermal change, just do it slowly. You could insulate your cylinder like crazy. You can. It'll help. But the other way is do it at room temperature and do it slowly. That's how you end up with no change in temperature. So this is slow changes tend to be isothermal. You want an adiabatic? Do it quick. I'm sorry, I said here you could insulate. I mean, don't insulate or, whatever. But here, just do it quick. Quick changes tend to be adiabatic. No time for heat to get in or out. I'd like you to be able to recognize or draw the traces for each of these guys. I'd like you to know the special thing like work equals 0, heat equals 0, etc. And beyond that, I'd like you to get right the fact that an adiabatic change is a steeper slope. I'm going to draw a little diagram to the side. There's my isotherms. That is not an adiabatic change. Adiabatic changes start off low, at low temperature, at big volumes, and go to big temperatures at small volumes. When you compress adiabatically, the temperature increases. In the original thing, this one I did here, when I compressed, I ended up going to a low temperature. So I want you to get that one the right way round. It's not a shallower curve than the isotherm. It's a steeper curve than the isotherm. I'd like you to be comfortable with those. Now, it's kind of interesting. It's actually for me anyway, it's kind of a very interesting time from a teaching point of view. What I learned and what our textbook said until quite recently was that delta E is equal to Q minus W. And we teach that. And if you look at my homeworks, I often say that. And that is because that's the way it used to be in physics. And I'd have people coming down from chemistry going, no, that equation's wrong. It's delta E equals Q plus W. And frankly, it depends on how you define W. And in chemistry, because they looked at things from the gases point of view, an expansion was always regarded as a negative thing. Whereas in physics, because we looked at things from the engine's point of view, we regarded expansion as a positive thing. So we had, for an expansion, a positive thing with a negative sign in front of it. And in chemistry, they had a negative things with a positive sign in front of it, and it worked out fine. The answer still worked out. It was fine. But each camp had to stay to their own equation and their own nomenclature. And then in more recent issue of Survey and Jewett, they changed to the chemistry way. Which I'm okay with. I think it's like, again, it's education sorting itself out. It took probably, this is probably 100 years. But, it's a little step towards consolidation. Unfortunately, I'm in that situation where half my work is the old way, and then part of it, first I was like, I'll just ignore it until I can change it all. And, I'm like in between now. I need to, oh man, I do need to do this. Your physics 1, I can do that, yes. I'm going to come along here. I can never remember how to do this. I need to insert a page.
Oh, you go to home.
Home.
Slide.
New slide, new slide, new slide. New slide. I've got to tell it. I'm going to put a couple in. And then I can go back here, slideshow, and from current slide. Okay. In the next room, there's a little dialog box which is to do with sharp pen, which is there all the time so I can do it. And I cannot find that software on this machine. They're supposed to be the same, and I just cannot find it. So I've got to try and I'm trying to transfer that software in so I can figure out what's going on. So let's say we have a volume of gas. And let's say that I add 60 joules of heat using Bunsen burner. And now my language gets kind of like vague. Expand the gas such that my internal energy decreases by 110 joules. Find work done. So I say, I'll do it both ways. Delta E is equal to Q minus W. That's what I wouldn't call the old way. And delta E equals Q plus W, the new way. In this case, I know that Q is equal to plus 60. And I know that delta E is equal to minus 110. And I say, well, minus 110 must equal 60 plus, minus W. So I say, well, W is equal to, I'm doing too many things at once. I'm going to say minus 170 is equal to minus W, so W equaled 170 joules. It was an expansion, so that was a positive W. So in order to get this cooling, when you're putting energy in, you have to do a lot of work. You have to expand a lot. It's not just a case of taking these two numbers away from each other. If you just take the two numbers away from each other, you get 50, and that's not the right answer. Yes?
So both work and Q are measured in joules?
Yeah. So in the next one, Q is equal to plus 60 joules, and delta E is equal to minus 110. So I go minus 110 is equal to 60 plus. Now this is an expansion. And from the new way, expansions are negative. Minus W. So we have minus 110 is equal to minus 170 is equal to minus W. So W is equal to 170 joules. So two different approaches to get to the same answer. Two different approaches to get to the same answer. In this case, I subtracted a positive value, and in this case, I added a negative value.
Why is the work negative there?
I'm sorry?
Why is the work negative?
Because from a chemistry point of view, they look at expansion as being a negative thing because they're looking at it from the gases point of view. And in a physics, well, traditional physics point of view, we looked at the expansion as being a positive thing. So because we had different nomenclatures for what expansion meant, we had to have different operators in our equations.
So in the new way, expansion is negative?
On a new way, the expansion is negative joules. Now you can stick to the old way. I can do both. But if you look at the book, it's going to explain it in the new way. Okay? If you're comfortable doing, how many people are comfortable doing the left-hand way? So do it the left-hand way. As long as you write down your equation, I know what you're doing. If you don't write the equation, it's just numbers. So, how many people doing the right-hand way? So, yeah. If you put both hands up, just pick one. If you put neither hand up, pick one and learn it. So this next little bit is really quite. This next little bit is really quite interesting. This next little bit basically is that we take a gas and we cycle it through a cycle. So we start and end at the same point. If we start and end at the same point, we have the same physical state for our gas in terms of pressure, volume, and temperature. Agreed? So it's unchanged. And yet we cycle the gas. And if we look at the amount of work, so in two cases, the arrow is pointing towards smaller volumes. These are compressions. And in two cases, the arrows are pointing towards larger volumes. These are expansions. And the work done compressing the first volume is that. And the work done in the second step is that. And then, I'm going to kill my diagram, but the work done in the third step is all of that. And the work done in the fourth step is all of that. But what we find is two of those works are positive and two of them are negative. So they subtract from each other. And what we're left with is the middle bit. And this is the work done. So the work done in a cycle is the area enclosed by the cycle in the PV diagram. So in effect, we got work out of our system. Where did it come from? Well, we had to heat to cause this change, and we had to heat to cause that change. So we have heat being done. Change in internal energy is equal to Q plus W. And what happens is our change in internal energy is 0. Because we started and ended at the same place. So now I'm going to say our Q is equal to minus W. The heat we get out, the work we get out was paid for by the heat. This is great. Normally, we do work and it inevitably goes to heat. Friction always takes you from work, a force through a distance, to heat. Kinetic friction, yeah? Sure. Kinetic friction is a one-way street. It takes you from mechanical energy to thermal energy. And there's no way back, typically. This is a way back. You can take heat and get work out of it. And this changed everything. This is the Industrial Revolution. This is the steam engine. This is the internal combustion engine. This revolutionized human experience. This is amazing.
There is no loss of energy either?
Energy is converted from one to the other. Is there friction in an automobile engine? You bet. Automobile engine is 1/3 efficient.
1/3?
Yeah, you put 10 gallons of gasoline in your engine, you get effectively 3 gallons doing useful stuff for you. The rest is heating up the environment and causing pollution. It's needless. It's disaster. You want a power station, 1/3 efficient.
So electric cars
You want a nuclear power station? Even less. Nuclear is a disaster. Yeah. It's even less efficient than a coal-fired power station. We pay all that money, and it's the only thing that happens is we don't have to carry as much fuel in. But we've got to live with the fuel for, well, I suppose you could live with we're living with the carbon dioxide for a long, long time, millennia, so maybe it's, neither one's good. So yeah, we have, and what makes it even worse, and just getting on an issue for me, what's even worse is, where do we put our, even power station, how efficient is a power station? About 30%. We stick it in the middle of nowhere, because people don't like the pollution. We transfer the energy across the countryside like it's going on holiday. It gets to us. In the meantime, we're dumping 2/3 of the energy as heat into the bay, or it used to be into rivers and streams and ponds, which killed the environment, by the way. There was a nuclear power plant near my college, and somebody, for a lark, released tropical fish into the outflow and then saw how long they lasted. Tropical fish in Britain in winter shouldn't last more than about 20 minutes. And they were there happily swimming in this little region of hot water coming out. That's changing the environment. And